variable. And variable covers the rest of the paths, which is from DC sweep to temperature, device parameter, DC sweep to temperature, source instance, DC sweep to source instance, device parameter, and finally DC sweep, source instance, and output as source instance. And this would be more clear as I demo each of these cases. So the first thing I'm going to do is I'll start with DC sweep, go to device parameter, and output a specific device parameter. And if you want to see a quick demo or see how these guys work it in action, you can always open a library called ef_examples. And so ef_examples has two test schematics, test_.dc 2D parametric device parameter. Okay. And this is what the template looks like. This is our process corner, the test circuit that we are going to evaluate. And this is what the template looks like. So I don't know if it is visible, but the DC sweep or inner loop is nothing but the DC sweep or inner loop, the x-axis that we are interested in. This is going to be the DC sweep. The next thing is the parametric sweep or the outer loop, which is this orange section. It could be device parameter in case of this template. And to give you a visual reference, it's going to be the parameters, like for parameter 1, parameter 2, parameter 3, parameter 4. Now the output, as we've discussed earlier, the output is going to be two cases, either the device parameter or the source instance. Now I'll just take a quick minute. What do you mean by device parameter? Now let's say you want to plot the drain current of M1. You can do it in two ways. The first thing is you can say M1 of ID. So if we look back at our schematic, this instance name is M1 for the upper transistor. The instance name of the lower transistor is M2. Now, if I want to plot the drain current, I can use device parameters, and I hope my screen is visible. If you can see, you have like a set of device parameters that ngSpice, the simulator, can decode and fetch you an output for. So if I say M1 ID, back here, if I say M1 of ID, so output device name, which is the name of the device, the instance name, which is M1, and output device parameter, which is the parameter that you're interested in. So if I say M1 in device name and ID in device parameter, what essentially I'm telling the simulator is, hey, for device M1, give me the drain current. And these are the other set of device parameters that a designer can plot when they explicitly state this in the so-called output field, that is output device name and output device parameter. And finally, these are the miscellaneous options. We have reserved these placeholders for some of the tricks or some of the options that we've decided could be a part of our future enhancements. But right now, let's just go ahead and run simulate. So if I can cross-check, what I'm looking back here is I'm going to sweep my DC sweep or the inner loop VVGS, that is the gate source voltage. And if I may remind, I have got two devices, M1 and M2, okay, cascoded. And the gate of both of these transistors is common. And I have a gate to source voltage I have a supply which is drain to source voltage set, and I can access this by saying VVGS. So VGS is the source instance name, and adding an extra V tells the simulator that I am varying the voltage of the source instance VGS. My DC sweep is going to start from 0 volts, stop at 3.3 volts with 0.1 volts increments. And then my parametric sweep is going to be the width of device M1. And I'm going to change my width from 1 microns to 10 microns with 1 micron increments. And what I'm going to do is I'll plot M1 of ID. So I have two ways. Either I can use some of these users use a voltage source and they say V is equal to 0 and find the current flowing through that voltage source. Or I can say that, hey, just give me the drain current of device M1. So without further delay, I'm just going to hit the simulate button. Now at this stage, because we are just going to plotting only one signal, which is M1 ID. So you'd be greeted with selected signal I@XM1. So this is what the simulator or ngSpice internally needs to plot device parameter. And this is how it is telling me that it has simplified this, vaguely garbled up device name into like something called M1:ID. And I'll just hit the return key and open the Simprobe. Now at this stage, I can either say trace, add, and if I'm interested to plot specific conditions like the drain current, that is M1 ID, when the width of M1 is 1 microns, or if I want to plot just the drain current of of M1 when the width of M1 is 8 microns, I can use control key and plot just two of these guys. That is the drain current when width is 8 microns and the drain current when the width is 1 microns. Or if I don't want to waste time, I can say trace add all, and it's going to plot the drain current when width is sweeping from 1 microns to, I would say, in this case, we've selected the trace for 5 microns. So that covers this path: DC sweep, DC parameter, device parameter. Now let's say you are not interested in device parameter. Okay, you already have Iprobe. By the way, Iprobe is nothing but a voltage source where the voltage is 0 so that you can see what's the current passing through that voltage source. So since a lot of designers have the practice of doing that, we've added something called as Iprobe, which does the same. All you have to do is just add this Iprobe at any branch. So in case when you have parallel devices, you can have Iprobes at branches of the specific devices that you need. And you can name it as, in this case, I've named it as branch current. Okay. And if I want to just look at the net voltages or probe currents, which in this case is branch current, or net voltages like M1_drain, or in this case, the net voltage is going to be common_gate_input. So I can ask this template to bypass this output and dump me just the net voltages or probe currents. So in order to bypass this field, that is the specific device parameters, all I can do is hit the control key. Okay. So let me just zoom in because it doesn't seem visible. I can hit the control key, select this specific field, device parameter. Okay. And now when I add the hash key or the pound sign, okay, hash key or hash sign or the pound sign, okay, what I'm telling this template is that don't use this output. Instead, just dump me all set of net voltages or probe currents that are present in this in this circuit. So once again, in order to do that, there is always an instruction that we've listed back here that how to do that. Like you can leave the value of field 17 underscore by using the control key and passing the pound character or hash key or hash character. And now when I simulate it, okay, I'll be presented with this user dialog, wherein I'm given all the possible net voltages present in my existing circuit. So in this case, I've got common underscore gate underscore input. I've got M1 drain voltage, M2 drain voltage. I've got something like net at the rate 7 voltage. And more importantly, I've got branch currents. So where it says current, that's where I have the probe current. Like wherever I've placed probes, I'll also have the currents passing through that probe listed back here. So at this stage, I'm just gonna quickly go ahead and plot the probe current by hitting. So if I want to select I of V branch current or the branch current probe, I can just go ahead here, hit the number 5 key, which is this guy. So I'll say 5 and hit the return key. That's when I'll be given a confirmation that, hey, I've selected the branch current. Okay, and I'll hit the return key again. Open the waveform viewer and say Control Shift Insert, which is nothing but add all. So at this stage, if you'll see, you'll have the branch current for width of device M1 as 2 microns or branch current for width of device M1 as 3 microns. If I, let's say, want to like rerun this simulation and plot what do you call the M2 drain voltage, which is nothing but the lower transistor, I can say 3, hit the return key, get out of this, open the waveform viewer, select trace, add all, and that's when it plots the M2 drain voltage with respect to ground, of course. The drain voltage with respect to ground back here. So that covers .dc underscore 2d parametric device parameter, which essentially covers this guy. And now a quick detour. Like let's say if I want to sweep the width of not only M1 but also M2. Okay. If I want to like concurrently or simultaneously sweep widths of both M1 and M2. In order to do that, I have a field in the parametric sweep or outer loop, other parametric sweep device. So when I've already stated that I'm sweeping the width of M1. Okay, and I also want to sweep the width of M2. I can just, change this field and say M2. So when I say this, when I change this field other parametric sweep device, now I'm telling the simulator to sweep the width of both M1 and M2 at the same time. And just to show the difference, what I'm gonna do is I'll just plot the drain current of M1 and sweep the widths of both M1 and M2 and look at what this output looks like. Oops. Adding all traces. So as you can see here, it is somewhere close to like 1.9 milliamperes when width of both M1 and M2 are swept. Okay. But when I say pass what you call a pound character or hash character and run this guy again, at this stage, it is just sweeping width of M1. It is not sweeping the width of M2. So my current passing through M1 instantaneously drops to something close to like 340 microamperes, if I'm not mistaken. Yeah, 340 microamperes. So this is how, you can be creative. You can say instead of width of M1, you can say length of M1. And bunch of other things, permutations and combinations that can happen in this parametric sweep loop, and especially the output loop. You are not confined to M1 ID. You can also say, hey, tell me what's the VTH of this guy. How does the VTH change? Okay. When I vary the length. Okay. And as I'm sweeping VVGS, I'm pretty sure VVGS is not going to impact, not going to affect the VTH unless we have some body effect. But we'll just go ahead and see if it works. And how does the plot look? Yep. So it also tells you like when you're varying the width, how does VTH change? And obviously this is nothing but the VTH is calculated by the device model. So if you are still interested to extrapolate VTH from ID versus VGS, you're more than welcome to do that. But if you want a quick overview of what does the internal VTH of the device model look like, you can pass a parameter called VTH in the output field. Okay, so the next thing I'm going to do is show you how this .dc_doody for parametric variable looks like. So far we've covered this guy. Okay, we are no longer interested in what do you call this. Now what we are concerned about is what happens when I'm parameterizing either the temperature or parameterizing either the source instance and looking at the device parameter as the output, which we saw M1 ID or the threshold of M1 or M2, or either one of the source voltages, net voltages, like for example the voltage of M2 drain, or probe currents, the main current, the main branch probe current. And similarly we can also sweep, like so far we did VVGS in the DC sweep. We can also do something like, hey, do VVGS, then do VVDS or unique set of VVDS values and plot me device parameters or source instance. So I'm just going to go ahead and quickly overview like how each of these conditions work. First thing, VVGS from 0 to 3.3, 0.1 volts increments. The first thing I'm going to do is I'm going to sweep the temperature from minus 25 to plus 125 at 25-degree intervals. And I'm going to plot the drain current of M1, which follows this path: DC sweep, temperature, device parameter. I'll hit simulate. It says M1 ID is stored. I'll go to the waveform viewer. Now at this stage, I'll just go ahead and plot all these guys by using the bind key, Control Shift Insert. And so what it does is like it will plot ID for VGS when temperature is for different temperatures, that is temperature at 0 degrees Celsius, minus 25, which is this guy. So this helps intuitively, like, when you look at what you call the drain current below VTH and the drain current after VTH, the tempo or the rate at which the temperature of the temperature affects the drain current changes, as you can see here. In case of plus 125, it follows this guy. And obviously, if you want to like just plot unique instances, let's say if I say add, I want to plot minus 25 and plus 125. I can do that. And let's say if I want to see what's the difference between these two guys. So what I can do is I can go to evaluate goal function. Okay. I can say, tell me the difference between this guy. I'm adding this. Then I'm saying negate. And then I'm adding plus 125. And I'm saying extreme difference. And I'm saying like, place it in a new exploit. So this tells me that, when you have this VTH, okay, there is no difference in the rate at which the temperature is, the drain current is changing. But, after my transistor gets into triode and gets into saturation and further into triode, okay, that's when the difference in drain current between those two extreme temperature begins to widen. So, these are the unique set of intuitive analysis that you can do once you have like multiple parameter outputs. This is something I just made up right away. That's something, I made up here. If I have this, what is it that I can do? So it gives you a freedom to plot multiple things at the same time and do these unique set of evaluations to get a better sense what the design or the circuit might perform, how the circuit might perform. Now the next thing that we are going to do is we'll do DC sweep, do a temperature sweep again, and this time we'll plot the source instance. So the same trick, I'm going to use the control key, select this field, double click, and pass the hash character or pound character. Say simulate. Again, I am greeted with this, what do you want? So since we don't have any unique set of voltages, I'm just going to go ahead and plot the probe current. So for return key, enter, plot, insert all. And this time, instead of using M of ID, which is the drain current of ID, I'm using the probe, the current probe, to plot the current passing through it. Now, you might ask, why do you need this current probe? Well, if you have multiple resistors, like let's say you have an array of parallel resistors, you can use this probe current branch to, you know, add this probe current to any of the resistors that you're interested to see what's the current passing through that resistor. Or you can also use something like a voltage source, okay? Sorry, a current with I of 0, and look at what's the voltage passing to the current source when no current, when I is equal to 0, to look at voltage between a capacitor. I mean, these are a lot of things that you can do, not at for DC analysis, but you can do this for AC analysis or transient analysis. So the next thing I'm going to do is cover this path, which is DC sweep, parametric sweep, source instance, device parameter, and source instance. And at this stage, I'll just go through quickly because we are already aware of how this template is structurally available to designers. So I'll change this to VVDS. So my x-axis or inner sweep is VVGS from 0 to 3.3 at 0.1 volt increments. My parametric is going to be from 0 to 3.3 and with step size of 0.33, so that we have 10 steps. And I'll say M1 ID. Insert all. So it plots ID versus VGS for varying VDS. Like when VDS, for example, this guy says that when VDS is 0.99 or 1 volts, you're sweeping VGS and plotting ID. The basic characterization circuit that you would desire, if you're evaluating your library devices. So if you want to be creative, what you can do is you can add all the NMOS devices from the PDK for this challenge in parallel and do this ID versus VGS for varying VDS. And you can compare how these unique devices, every NMOS or NMOS RF performs. You can stack these two guys against each other and see their performance and decide, which device to go with. I know NMOS RF is not good for analog, but there might be something which is worth looking at. And at this stage, if instead of M1 ID, I want to see what does the branch current look like, I can replace it with hash character or pound character and simulate it and say, okay, I want to plot branch current. There you go. Instead of using M1 ID, I'm saying, plot me the branch current of branch underscore probe underscore one, which is essentially this guy. But the most interesting thing is the output parameters. Like when you say device parameter M1 ID, you can say device ID, device VGS, device VDS, device VBS, GM, transconductance is sometimes crucial. So let's say if you plot ID versus VGS and you don't want to use the derivative function, you can just go ahead and plot M1 GM instead of plotting ID VGS using the derivative function. You can plot VDSAT, VTH, calculated by the device, of course. Then you can, plot CGG, CGD, CGS. CGG is crucial for input capacitance, the gate capacitance. CDD, when you're looking at the drain, what's the effective capacitance at the drain? And you can plot the bulk charge, the gate charge, the drain charge. So let's say like when you're doing like 0 to 1, and if you want to see what's the charge leakage at the drain, you can individually plot the charge to look at the charge leakage. I mean, this is something which can give you an intuitive sense what the leakage looks like or what's the VTH variation when you are sweeping the temperature. And another thing I wanted to cover is that so far, in both these templates, we have been sweeping this inner loop as DC sweep. What if you can sweep this inner loop or the x-axis as temperature, and we can do parametric sweep of either the device parameter or source instance. So I'm just going to go ahead and quickly show just one of these parts. Okay. I mean, it's just a minor modification. And the reason I want to show you this is it gives you an extra power as a designer. So at this stage, I have this .dc_2d parametric device parameter. I'm going to change this guy to temperature, change its start, stop, and step conditions. Start at -25. I mean, this is really helpful because in a temperature sensitive circuit like bandgap, you always want to look at for the temperature sweep on x-axis, and when you're changing the parameter, how does this look like? So let's say sometimes you have a hard time selecting these guys. You can always click on this if you have to change multiple parameters. You can always double click on that template, and you can go by these unique field names. So I can say I'll change the field value of 2 as -25, field value of 3 as +125 and 25. Now I'm changing the M1 length from 1 microns to 10 microns. And I'm saying with 1 micron increments, and I'm saying M1, I want to plot the threshold voltage of M1. Now, when you are doing DC bias or when you are setting your DC bias conditions, you might want to look at if I'm sweeping the temperature range, how is it that this guy looks like? So this says that when I'm sweeping my temperature from -25 to +125, the temperature, the threshold voltage, okay, linearly drops. And for length of 1 microns, the threshold voltage is higher than for the one wherein the length is 9 microns. I can be creative and go ahead and say, for example, I don't know if this is going to give any fruitful result, but let's just give it a try. So there's no change in CGG whatsoever. Oh, I'm sorry. My bad. I tried to change, what do you call, um, the device parameter as CGG. I'm supposed to plot CGG as the output. So output device name M1. So yep, CGG does change from 26 femto for 9 microns all the way up to 3.5 femto for 1 microns, the length of the device. So that's pretty much it. I mean, you can always be creative and change either the device parameter or the source instance and plot M1 VTH, M1 ID, or probe currents, net voltages. Probe currents, net voltages again for by changing the source instance and keeping the x-axis as temperature sweep from -25 to +125. So that's pretty much it. That covers these 2D sweeps or parametric sweep templates and the ways you can hack it to get plethora of plots to analyze stuff. At this stage, we'll open up for any questions. Questions?
Can I ask a question?
Yeah, go ahead.
The question actually is not about the parametric sweep or device sweep. I just have another question related to the stability analysis and the loop gains. Do you have an idea how to do stability analysis for a loop and how to get the open loop gain?
Not at the moment, but I'll just make a quick note on that. Yeah.
Because it's very crucial, really. I wanted to see if the loop that I have is stable enough or there's something wrong. I want to see the loop gain to see how I'm going to be good or not in the supply rejection or so. Yeah, I want to do stability analysis and I don't know how to do it.
Okay, a quick question. Cutting the loop of your current circuit and then analyzing it using Bode plots won't suffice, right? Would it?
Again, please.
So let's say you have your closed loop, your feedback system. So can you cut the feedback system, make it an open loop system, plot the Bode plot, and then manually visualize the stability, looking at the phase?
Yes, but you have to. I think you have to maintain the operating point, and also you have to take the loading effect of the different parts of your circuit that you're gonna cut. And so those all things. I want to see how the loop is going to behave according to stability analysis, like we do usually in like in Eldo or in Cadence, or I mean,
Okay.
there are
You
things like
mean the stability circles, right? The stability circles on the Smith charts.
Sorry?
Are we talking about those stability circles uh, impedance impedance Smith charts, or those
No,
loop?
the loop gain, yeah,
Okay.
and the Boolean blocks. Yeah.
On booty plots, right? Okay, yeah. We'll definitely
Yeah.
look into it. I'm pretty sure there is a way, but we'll definitely look into it and cover it either as a separate offline discussion or probably bring it up during the next.
I can see it's there is .bz. I think it's full zero, but I don't know how to use it, or if you
Dot
have
BZ,
used.
right? Dot
Excuse me.
PZ, the pole zero, dot PZ, pole zero analysis. Okay, yeah,
Yeah, that might have something related to the stability analysis that I'm talking about, but I
okay,
don't know how to do it.
sure. All right.
It will be good if you explain it. Even it doesn't have to be in a seminar or in a webinar, sorry, but it could be in an article, like you're doing such articles in the challenge knowledge. I think it's
Okay,
called open knowledge area. You can put something like that, how to do the stability analysis.
okay, sure.
And also, I want to ask a question about the sweep. If you swept all of these parameters and you have the output like you had, can we have these outputs like in a CSV, I mean in tables or in a text, so that we can manipulate these texts using something like a Perl script, so that I can make a function to look at some parameters at a specific other parameters. For example,
Yeah,
here.
something like cross. Sometimes in Cadence you use something like cross and tell me like what's the x value. Is that something?
Yeah, I may make a function
Mhm.
using Perl script, and I let the function help me to find y value at x value, or this can help in the GM over ID if I'm going to
Yeah,
design using GM over ID method.
exactly.
So I used it before, and I used Ocean to do that
Hmm.
um, with the help of Perl script. And I've done it also on the HSpice before. So I'm just asking, I'm wondering if we can do it here, like having text files, having these kind of tables, and let a Perl script to look at
Okay.
uh, values. Yeah.
So there are two what do you call open ends to this. The first being like the way we generate raw files. Okay, is we have a specific syntax to that raw file. Okay, and
Yes.
we can always say that. So every parametric, like say for parameter value 1, for parameter value 2, we have a raw file with signal vectors in that raw file.
I got it.
Okay, and option number 1 is like if you have your Perl script implementation to do these expression level things on these existing signal vectors, yes, we can uh, we'll need a day or two to open up a way wherein you can either say that okay, plot me using the Iprobe waveform viewer, or you can access those individual raw files and then you can use it on your own Perl script, if you have it ready. Or the second option is we have something called as future release fields. So one of the things is what we were planning is like, let's say M1 of GM, M1 of ID. I know like GM over ID is so crucial for basic characterization versus width on the x-axis. So what we are thinking is like, because for webinar, like we wanted to show what the basic set of things are needed. We wanted something like M1, GM, M1, ID, and then we would have a field wherein you can use these guys to create an expression in ngSpice. Like you can say 17 divided by 19 and plot me that and save that as the output. So you can also do that.
Mhm.
You know, you can, and that expressions, like you can use ngSpice expressions. I mean, I've seen somewhere, if I'm not mistaken, in, I believe in one of these, like, so they've used when conditions. So you can also say like, I mean, this is just a hypothetical situation, like M1 ID when, I mean, M1 ID when uh, M1W is 1 microns. Okay. So you would have y-axis condition, x-axis condition. So M1 ID when VGS equals 2.4 volts. Okay. When
Yes.
um, M1 width is 1 microns. So it will say like, what's the drain current when VGS is 3.3 for width so and so. I'm pretty sure that's something that a designer would want. Hey, I want this, or I want to limit this, like, you know, between this range, what are the set of options, the drain currents or the threshold voltages or whatever, like, you know, I mean, there are zillion combinations. So that's what we were planning for future, because we were so like tied up answering help desk questions and, you know, integrating this post-processing script for our waveform viewer.
Yes, I believe I was actually using the Perl script, and I put all the vectors of the GM over ID, CGG,
Okay.
or C over CGS, and the other parameters of the GM over ID method, and I put them all in table, and then I use a Perl script to look at any value at any other value, like GM over
Yeah.
ID at a specific V over drive or something else. I can pick any value from any value, so it was really very helpful. Yeah.
Okay. So comma separated value, that's something that we'll have to look at, but we can quickly, like, you know, give you this thing, like the way you can do it is like you can have uh, a separate raw file for unique parametric conditions, and each raw file would contain the signal vector that you've asked this template to. And I agree, like, you know, sometimes you want to look at your long channel equations and guesstimate your long channel equations, write down your long channel equations as expressions and get these parameters or voltages and create an expression out of it and evaluate it, like using that long channel equation of ID or looking at gm.rd or gmro or gain bandwidth.
Yes, you're right.
Yeah. So yeah, we had that in mind. So that's the reason, like, you know, we have these, hey, for future release only. It's just that we are trying to integrate it in a day or two, create an option wherein you can access those raw file for unique set of parameters. Yeah.
Okay, thank you very much.
Okay. Any suggestions like that besides stability and
I don't think so. It was just the stability. I couldn't do it.
pole
So
giving, right?
yeah.
Yeah. Okay. And a quick question: would you need any, what do you call, device parameter level sweeps when it comes to pole zero analysis? Like sometimes on root locus we change the gain of, I mean, this is from my root locus understanding, that when we have root locus, we vary the gain of the system. And by vary the gain, I would vary the, yeah, gain of my system and look at how my poles are behaving in my stability circles. So do we need any parametric sweeps around or sweeps around stability templates, Ibrahim? Do you think we would need that, or we are
No,
just looking at,
no. It's more simpler than this, I think. It
okay,
just, yeah, the booty plot would be very enough, I think.
okay,
Mhm. Yeah.
all right.
At least me, if somebody else has any questions, they can do it. But for me, actually, I just need the stability, the loop gain, booty plot.
No, absolutely. We're trying to understand, like, how designers like need, like what kind of tool sets they need, what do you call, in their tool tool belt. So yeah, that's a lot of help. Whole zero. Okay. Any?
Yeah, if you have any way to force the circuit to be operating at the right operating point, and I can break the loop, or do you have any ideas? I think you can just put an article, or you can launch another webinar
Okay.
or anything, because it will be very, very helpful, because I really in a big need for this.
Yeah. So a quick question. When you say like operating points, are we talking about initial conditions? Like
Yeah, in
like
the DC operating point at which the circuit finally got at. I mean, if you have a loop, and then this loop will be at last stable at some voltages, and you know these voltages.
okay. All right.
So I want to see the loop gain at these values of DC operating point for the different nodes in the loop.
Okay. All right. Sure.
Okay.
Any further questions? All right. So
I just remembered something. You showed.
oh shoot, Rajiv. Ibrahim.
Hello.
Hello.
Can you hear me?
Yeah, we kind of like lost you for a second.
Yeah, I was saying that you mentioned something like the test benches that are used in the characterization tool, and we can access those kind of test benches, right?
Yeah.
Are you sure that the test benches are the same that are used in the characterization tool?
Yeah. So exactly, and it might look absurd at the very first stage, because when you're looking at test bench and SPI, okay, you're just looking at variables, okay, but the values defined for these variables are stored in something called as JSON file under the project directory. So the JSON file contains all the values, or the values for the variables used inside the test benches.
Mm-hmm.
So yeah, I mean, at first stage when you look at it, and some of these test benches, if I'm not mistaken, and I must add that I would have to confirm it with Tim Edwards, who was the brainchild behind this test ACE engine. Like, he uses some of these test benches, like results generated from some of these test benches, mixes it up and creates unique set of plots that you see in the characterization tool. But So far, if you open any of these test benches, all these variables, using $sign and curly braces, these variables get their values passed on from the JSON file. So yeah, but you said something like if we are using the same set of test benches. Yeah, we are using these test benches when you're running your simulations locally using the ACE engine.
Okay.
Yeah.
Yeah. Mhm. Thank you.
Yeah. And just to reconfirm, like the JSON file is not in the test bench directory. So if you go to design and your project directory, it's going to be on the topmost level JSON file. But bear in mind, like if you're changing this JSON file, okay, when you submit your design to the ACE engine on ACE server, it is going to like evaluate your circuit for the defaults that are the
Yeah.
default values for. Yeah, so like sometimes it happens that some users might want to like change these values to limit their conditions, and then when they upload it, like their suddenly their design fails for certain corners. So yeah, that's what is a key point. More questions?
No, thank you.
All right. Thank you, everyone. So we hope to see you all in the next webinar, and please keep on checking our knowledge base because we'll be adding bunch of improvements, enhancements based on the feedback that we received on help desk as well as webinars. Thank you all.
Thank you.